Right, so this is covalent bonding, video number 2. I realised I got cut off in mid-flow in the first one, just as we were drawing the cross and dot diagram for carbon dioxide. So we can see that carbon over here needs 2 electrons, oxygen here needs 2 electrons. So we'll combine our diagrams that we started to draw before. So here's my carbon bonded to the 2 oxygens. I'm going to draw the cross and dots in different colour just so it's slightly easier to see. So here are these 2 electrons. They're going to go here and here, and I'm bonding them with these 2 electrons here. So there's one pair and there's the next pair. And then we've got a pair here and a pair here not involved in the bonding. And the same can be true on the other side. So a pair here and a pair here. Make sure it's nice and clear that it's a cross and a dot. I'm using a pen which is a bit thick. And then we've got a pair of electrons over here, and a pair of electrons from there, down there. So you can see that the oxygen, which originally had 6 electrons, 2, 4, and then those 2 there, 6, has now gained another 2, so it's got 8. It's now nice and happy. This oxygen here is in the same situation, and the carbon, which originally had 4 electrons, those 4 dots, now has 8 electrons, so is itself happy. I'll just show you the shorthand. So carbon double bonded to the oxygen, carbon double bonded to the oxygen there, and that's carbon dioxide. Now we also need to be able to draw cross and dot diagrams for 2 hydrocarbons. So hydrocarbon being a compound that's only made of carbon and hydrogen, and the 2 on the syllabus are ethane and ethene. So ethane being an alkane, and ethene being an alkene. And obviously those of you who have done the organic chemistry part of the course will be thinking, ah yes, ethene, it's an alkene, it will react with bromine water to make a colourless solution from an orange solution, which bromine water obviously is at the start. Now when we're drawing these, I recommend you start with the carbons. And here's the 2 carbons, and we've got 6 hydrogens. Now if I've started with the carbons here, let's draw my 4 carbon electrons on. They're the 4 for the left-hand carbon, there are the 4 for the right-hand carbon. And now we can pair up the hydrogen electrons with the carbon electrons to make complete outer shells. Now remember that carbon is in group 4 and hydrogen obviously in group 1, so it only has 1 electron, so it can only donate 1, but the hydrogen only needs 1 more electron in order to complete its outer shell. So therefore if you work round and you look at the carbon, you can now see that this carbon here has 8 electrons in its outer shell. This carbon here now has 8 electrons in its outer shell. Each hydrogen only has 2, so they are complete. Now ethene is slightly more complicated. You've got less hydrogens in there, so and this all looks very complicated until I label it. I bonded initially 2 carbons together, and then I put my 4 hydrogens on. The hydrogens we know form 1 covalent bond, and actually hydrogen can only form 1 covalent bond. So that's taken 2 of the electrons that carbon originally had, carbon originally having 4 electrons. So let me put 1, 2 there. And the same is true on the other side. This carbon originally would have had 2 electrons, and here's the remaining 2, forming a double covalent bond between the 2 carbons. So if we were going to write this in a displayed formula, we would show the single covalent bonds up here, and now we can see that we form a double carbon-carbon bond over here, and that's the shorthand way of writing it rather than writing out the full cross and dot diagram. Very frequently asked cross and dot diagrams, very important, you can draw them, and you must have your periodic table in front of you and all the time be looking initially at how many electrons are in that outer shell. Now, all the covalent substances we've been looking at thus far are termed simple covalent molecules. Okay, they're all referred to as simple covalent molecules. That's a type of substance. And you can see here, these are ammonia molecules. And what you can see is that here's one unit of ammonia, one ammonia molecule, here's a second, and here's a third. And between the molecules, they actually have very weak forces of attraction. So it's very, very easy to take this ammonia molecule and move it away from this one. They only have a very weak force between them, so it doesn't require very much energy to pull this ammonia away from this ammonia. And that means that simple covalent molecules have low melting and boiling points, even though the bonds within the molecule are very strong. So frequently asked, why do simple covalent molecules have such low melting and boiling points? Usually they say they give a molecule. Why does nitrogen have such a low melting and boiling point? Why does methane have such a low melting and boiling point? And the reason being is because of the weak forces between the molecules which are there. So only a small amount of energy is required to overcome the force. It's not on the syllabus, but you should also be aware that simple covalent molecules are generally insoluble in water, and this is very much on the syllabus. They don't conduct electricity, and the reason they don't conduct electricity is because they do not have, there's no delocalized electrons like in metals, and there's no free ions like when you have an ionic substance which has melted or been dissolved. It's therefore an ionic substance at that point has free ions which can carry the charge. So this one here is very much the key point here. Why do they have low melting and boiling points? The reason is because of these weak forces between the molecules, and because these are so weak, we can very easily pull the molecules away from each other. We can separate them, and therefore they have a very low melting and boiling point. Now there are a couple of other covalent structures that aren't simple molecular, and one such example is diamond. Okay, and diamond is an example of a giant covalent structure. I'm not too keen on the green highlighter, it seems to have obliterated half the text. But giant covalent structures are a very popular example of covalent structures that aren't simple molecular, and diamond being one of those. Now diamond is an allotrope of carbon. Every atom within diamond, and here's a diagram to show it. This is you can see it's quite a complicated diagram. Every atom within diamond is carbon. So if I just pick one atom here, and I'm going to use the black pen for this, we're going to pick this atom here, and you can see, hopefully, that we've got one bond, two bond, 3 bond, and then a 4th bond coming out. And this then bonds to another carbon atom. Now, because I've chosen one on the edge, which are easy to see, you then see that the ones it's bonded to don't actually follow the 4 bond rules, but they should do. They should have 4 bonds in all different directions here, and you can see, sorry, I just someone's coming in at the door. Anyway, each atom at the edge still continues to form 4 bonds to ones elsewhere, and I've made a bit of a mess of this, but hopefully you can see if you look at other bits of the diagram and pick on a molecule, pick on an atom even. Let's pick on an atom up here. Let's pick on this atom here. You can see that this is also bonded to 4. 1, 2, 3, 4. Now, because each atom is bonded to 4 others in very, very strong covalent bonds, that gives diamond a very, very high melting point, an incredibly high melting point. It also makes it incredibly hard. Okay, you need a huge amount of force to break a diamond, because as soon as you start applying force here, you're pushing against not just one covalent bond, but you're pushing against millions within this giant 3-dimensional structure. So the atoms just won't move because they're held in place by millions of covalent bonds. Likewise, when we try to boil it, when we heat it up, we're not trying to, the heat doesn't just go into breaking one covalent bond, it has to break hundreds, thousands, millions of covalent bonds all over the place. So it gives it a very, very high melting point. And these are key points. High melting point, and the 4 points you need to make there, or the points you need to make there, each carbon atom bonded to 4 others. And if it's going to be a really good answer, each carbon atom is covalently bonded to 4 others. So there are millions of covalent bonds in a 3D lattice. So a huge amount of energy required to overcome the bonds. Now, diamond isn't the only form of carbon that we know. There's another allotrope of carbon, which we look at GCSE, which is graphite. And in graphite, each carbon only bonds to 3 other carbon atoms. Now, carbon, you know, is in group 4. So 1, 2, 3, 4. And if we just pick on this atom here, you can see it's bonded to 3 others. So we form a bond there, form a bond here, and form a bond there. This electron is left unpaired. And what happens to this electron is that it's allowed to wander up and down between the layers of carbon atoms. So what we have is a very different structure to diamond. We have each carbon bonded to 3 others. Now this means that in the same way as diamond, it has a very high boiling and melting point for exactly the same reasons. But because of the layers of hexagons, which I'm hoping you can see in the diagram, the layers of hexagons have got these delocalized electrons between them. This means, just like a metal, the layers can slide, therefore the graphite can act as a lubricant. It actually has a slippery feel because the layers can slide over each other. It also means that the graphite can conduct electricity because it has these delocalized electrons in the middle. And those two are very, very important points. It's slippery because the layers can slide over each other, and it conducts because of the delocalized electrons.